Hello and welcome to the course Signals and Systems. I am Dr. Zishan Karim from Electrical Engineering Department, CUIWA campus. Okay, let's discuss the lecture contents. In this video, we will cover signal classifications in detail. So, classifications of signal. Usually signals are classified into several categories depending upon the criteria used for its classification. However, in this we will just look at continuous time signals. What does it mean? I think you will be much familiar with the continuous time signal. If a signal is defined for all values of the independent variable time t, it is called a continuous time signal. For example, look at this picture. Here on x-axis we have a time t, and here signal values, for example on the y-axis, this is a signal as xt sine pi t. So on the y-axis we have a value for each time t by calculating sine pi t. So we get xt. So on the y-axis we have a xt. So for each value of time instant, like for example starting from t equals to minus 2 to t is equal to 2, right? So from minus 2 to 2 we have a value at each time instant. Each time instant means very small interval of time. For example 0.001, if we take like this, for example. So we have a continuous wave here, and for each time instant we have a value of a x of t. So this is continuous time signal. Since these signals vary continuously with time t and have known magnitudes for all time instants, they are classified as continuous time signals. As you can see from this picture, that for each value of time t there are magnitudes for each value of against the each value of time t. So this is called a continuous time signal. Here we will discuss discrete time signals. In the previous slide I mentioned that the time is continuous, then it is called a continuous time signal. Here, as the name suggests, the discrete time, it means we have a time values taken at a discrete interval. Like for example here -8, -7, -6, -4, -5, -4, -3, -2, so on up to 8, right? So from -8 to 8, but the values taken at time to instant taken was just at some interval. For example, from -8 to 8, but with the step of 1, right? 1 was the step taken. So from -8 to 8 with the step of 1, if we put these values in the sine 0.25 pi k, so here because the time is discrete, so in discrete we usually represent by k. So when you put this value, for example x of -8, because k will be 8 here, -8 here, in this way you can calculate the magnitude of a discrete signal. So sine 0.25 into pi into -8, right, to -8. So after calculating this you will get some value. Here I think we will get 0, so we have a 0 here. So x at -8 will be 0. Similarly x at -7 there will be some magnitude, and x at -6 it will be equal to 1, right? So on. So this is called a discrete time signal because here we have a amplitudes at discrete values, and the time taken was the discrete time instant, right? This is an example. Consider the continuous time signal xt is equal to sine pi t plotted in a figure previous as a function of time t. discretize the signal using a sampling interval of 0.25 second and sketch the waveform of the resulting discrete time sequence for the range k greater than -2 or less or equal to 9. So what we have to do, we have a time instant sampling time of 0.25. Look at this, and the signal is sine pi k. So by substituting t equals to kt, because this is a discrete time, so t is replaced by k into sampling time. Why sampling time? Because we need to sample at some time instant, so that time instant is fixed, so 0.25, and like the sampling period, so that period is 0.25 second, and k represent exact time at which the sample is taken. So t is a period, right, and k is the exact time at which sample is taken. So we will replace t by kt here, right, sine pi t, because we have a sine pi t, so we replace t by kt, and whereas the value of the t is 0.25. So the signal becomes xkt equal to sine pi k into 0.25 equals to sine 0.25 pi k, right? Now we need to plot a discrete time signal. So values can be 0, plus 1, plus 2, so on. So we can start, here we have an example taken at x is equal to -8. So -8t, so sine equals to sine -2 pi, which is 0, right? Similarly x minus 7, so x minus 7t, so sine minus 1.75 pi is equivalent to minus 1.755 pi. So it results in 1 by under root 2. Similarly, you can calculate for x is equal x1, x is equal to t, so sine 0.25 pi. So better to ignore this one and just focus on this equation, right? So we have a sine 0.25 pi and 1. Instead of k we have a 1, so sine 0.25 pi. Similarly x2, so if you focus on this equation, so just put, instead of k, put 2 here. So sine 0.25 pi into 2, so it becomes 0.5. So resultant amplitude will be a 1. So on. So these are all values are taken for example -6 to -1 and then 0 and then 3, 4, 5, 6, 7, 8. So this was a continuous time signal given to us, and we need to convert into a discrete time signal, so which look like this signal. So this was an example to show that how we can discretize the continuous time signal into a digital or discrete time signal. So there are different types of signal, as we already discussed. Um, for example, in figure A, it is called analog and continuous time. Why is analog? In analog, the information is in every time instant. Like each part of the signal have a information, and you need to, for example, this. So each part of the signal has an information, and it is called analog. And with respect to time, it is continuous. You can see that there is at each time instant there is a value, so it is a continuous time. So it is called analog continuous time. The second one, there are levels, right? You can see that the levels in this way, this, so on, right? These are levels. So this is called digital and continuous time. But you can see that the x-axis time is continuous. There is no break in the time, right? So it is with respect to time, it is a continuous, whereas with respect to shape or the amplitude, it is digital, because they have a levels, and there are only information residing in the levels, not in each part of the signal. So this is called a digital and continuous time. The other one is the analog, because you know that this is analog signal, but it is discrete time. Analog and discrete time. So this is analog, but time instant we have taken at some time instant with a interval. The interval is fixed, right? So we called it as a analog and discrete time. The last one is the digital, because you know there are levels, right? This one, this one, then again this, but digital and discrete. So digital means the levels are there, and discrete means we are taking at some time instant. So discrete always means that we are taking at some time instant, right? Like this was the analog in nature, but we are taking at some time instant, not continuously, so it is called a discrete. So these are the four different types of a signal. Other term is the periodic and aperiodic signal. You are much familiar of these terms because I think you are studying these courses several times. Previously you studied different courses number of times, and that you studied this concept. So a continuous time is said to be a signal is said to be a periodic if it satisfies the following property. So for a continuous time signal x of t, so it means that the time axis it is continuous and signal is a continuous with respect to time. So it will be called a periodic if it satisfies the following property. This is your x of t signal. So if we repeat it after x t plus some time interval or time period t naught, so it looks similarly like what it looks at xt, then it is called periodic signal. For example, you are much familiar with the sine wave. It's an easy example to explain. So this is starting at 0, right, and ending at some value. So if it is a called periodic, if it repeats after time interval t again, right? So this, and if again it repeats, continue this, and for example, if we start from here and end here, this is time t naught, right? This is time 2 t naught, so on. So if you look at this portion, this is similar like this one. So on, it will carry on. So it is called a periodic signal. At all time t for some positive constant t naught, the smallest positive value of t naught satisfies the periodicity condition. Equation 1.3 is referred to as a fundamental period of the t. So we call it as a fundamental period. So fundamental period usually mean that it is the your basic period, because uh, based on this you will have an harmonics like 2t, 3t, these are called harmonics. Fundamental is your basic time period. Likewise, in a discrete time signal, x of k, for example, is said to be a periodic if it satisfies the condition xk equals to xk plus k naught. Here we have a period k naught. So kl time k for some positive constant k naught, the smallest positive value of k naught that satisfies the periodicity condition. So equation 1.4 is referred to as the fundamental period of xk. So it is called the fundamental period. A signal that is not periodic is called an aperiodic or non-periodic signal. So figure shows some example of both periodic and aperiodic signals. So the other time is the fundamental frequency. That's the reciprocal of the fundamental period, as we have a fundamental period t naught. If we take the reciprocal like this one, 1 over t naught, so it is called the fundamental frequency. So fundamental frequency 1 over t naught for continuous time signal, fundamental frequency for discrete time signal is 1 over k naught, right? So t naught and k naught are respectively the fundamental periods of continuous and discrete time. The other term is angular frequency, which can be calculated as 2 pi over t naught, using fundamental period. So it can be calculated as 2 pi over t naught. So similarly, it is for continuous time signal. For um, discrete time signal, we have a ohm naught equals to 2 pi over k naught. Instead of t naught, here we have a k naught for discrete time signal. A familiar example of a periodic signal is a sinusoidal function represented mathematically by the expression. So this is our periodic signal. This is a familiar, very much known example of a periodic signal, as I plotted in the previous slide as well. A sine omega naught t plus theta. So this is a periodic signal which is repeating after some time interval t. The other important terms are deterministics and the random signal. You must know these terms because in wireless communication or any communication, these terms are very much popular. So deterministic, if the value of a signal can be predicted for all time t in advance without any error, it is referred to as a deterministic. What does it mean? For example, I have a sine, right? Signal sine pi t. If we have a signal sine pi t, this is mathematical expression. So can you predict the value of sine pi t? Yes, of course, by putting different values of time. For example, time 0, time 1, time 2. So when you put time 0 here, you can get output exact value. For example, at time 0, you will get 0, right? So it is exact. Like at time 0, we have an amplitude of 0. When you put sine, for example, 1, so pi into 1 to sine pi, again you know the exact value. So sine 2 pi, you again know the exact value. Not you are not confused what will be the value of sine pi t. You can just take a calculator and calculate the exact value. So these types of signals are called deterministics because we can calculate the exact value in advance without any error, because we know the exact value, so there will be no error. So it is referred to as a deterministic signal. So deterministic signal can generally be expressed in a mathematical or graphical form. Some examples of deterministic signals are as follows. So these are called continuous time sinusoidal signals. So x1 t 5 sine 20 pi t plus 6. So you put here time t and you can get x1 t. So this is continuous time signal, but it's deterministic. So other one, continuous time exponentially decaying sinusoidal. So if you just put t here again and calculate 2e minus t here as well. So 2e minus t sine 70. So you will get exact value of x2 of t. So these are types of signal are called deterministics. Now the other term is random signal. Random actually in wireless communication or the communication used as we have a wireless channel, so we don't have a deterministic signal anymore in the channel side. So here comes the use of the random signals game. So conversely, signals whose values can't be predicted with complete accuracy for all time are known as the random signals. You studied probability, and other distributions. The only reason for studying the probability and the distribution is to check the randomness or to model the randomness or the random behavior. So this is where random signals or the randomness came. To model to know the what kind of randomness exists in the signals, you have a probability density function. So these random signals can just be characterized by a statistical measures such as mean, standard deviations, mean square values, variance, etc. So to measure the random signal, we can't exactly calculate the what will be the value of the random signal at time instant t. But by using some statistical measures such as mean, standard deviations, mean square values, we can calculate its randomness or its output, but it will not be exact as in deterministic signals. So here we can use the probability density functions and so on. So in electrical engineering, most meaningful information bearing signals are random signals, as I mentioned just a while ago. So in digital communication system, for example, data is generally transmitted using a sequence of zeros and one. Thank you for listening. And for question answer, there will be a separate session and the exact time and date will be communicated later on. Thank you very much.